In this video, we want to talk about the importance of the absolute refractory period in cardiomyocytes. And we've already seen the cardiomyocyte action potential, right? This is the one with this big long plateau here. It's phase 2, right? Due to this opposing potassium and calcium flux, right? We've got two sets of channels that are open at the same time here. And of course, potassium is leaving the cell, calcium is entering the cell. And because our VM, our membrane potential, is staying reasonably constant, right? It's falling a little bit maybe. We know that they're essentially balanced, right? Now, why is that important? Why do we, right? In other words, if we were to draw a neural action potential, right, sort of adjacent to this, it would look like this, right? It would last, a millisecond or two, right? Look at the time down here. 200 plus milliseconds for the duration of this action potential. Why such this enormous duration of an action potential? And honestly, if we could draw a neural action potential and a skeletal muscle, let's draw that, skeletal muscle action potential, right? Maybe even the better reference, right? Looks very similar, right? A couple of milliseconds long. Now, why this extended action potential in cardiomyocytes? And the answer is twofold. It is protective of function and protective of pathology, right? So in the way that it's protecting function. So let's go over to our skeletal muscle action potential here, right? This is like skeletal muscle, right? That's our action potential in a skeletal muscle fiber. The tension that's developed in response to this skeletal muscle action potential, right? In other words, keep in mind, right? You might have forgotten this, right? Neurons generate action potentials, but so does cardiac muscle, so does skeletal muscle. And the skeletal muscle action potential would be like this first spike going up and then coming right back down. It would take a couple of milliseconds, right? So it's dramatically different. It does not have this prolonged plateau phase. Here's the why, right? In skeletal muscle, that action potential, as it is in cardiac muscle, the action potential is the stimulus for contraction. But in skeletal muscle, if this purple line is tension, tension is delayed, right? In other words, that action potential is so fast that the excitation contraction coupling mechanism, in other words, getting that action potential to lead to a rise in intracellular calcium, to lead to sliding filaments and tension development, it takes so long for those, and again, long, a couple of milliseconds, but it takes so long for that to happen that the tension, right here in purple, doesn't happen. The twitch, it's called, right? The twitch tension doesn't rise until after the action potential. So that leads to the basis of tension development in skeletal muscle. Twitches do almost nothing in skeletal muscle. The heartbeat is a twitch, right? So twitches in cardiac muscle mean everything. They are the heartbeat. Whereas in skeletal muscle, this twitch tension lasts, 10 to 100 milliseconds, maybe 200. Well, how many things can you do in life that take you less than 0.2 of a second? Blink, right? Not much else. You're not getting out of a chair in 0.2 of a second, right? And so what we have to have is repeated action potentials, right? Have these action potentials repeat themselves, right? And actually, maybe I should put this a little lower so I can superimpose my muscle twitches, right? If we have our action potentials repeating themselves one after another, right? What's going to happen is our tension, we're going to get that twitch, we're going to get that first twitch, right? And then that second action potential occurs, and you're going to get the second twitch, and you get the third twitch, and I'm drawing these too far apart, right? You're going to have them stack a little faster than that, right? First twitch, second twitch, third twitch, fourth twitch, right? On and on and on until some maximum is reached, right? And that's of course called tetanus, right? Where the twitches are stacking together and tension is growing, if you recall, that's called wave summation, right? So that this first twitch is just this first little blip down here, right? We have to add twitch after twitch after twitch on top of one another, right? Not losing tension, or at least not dramatically losing tension in between them to generate real tension in skeletal muscle, okay? We don't want that to happen in cardiac muscle, which helps explain this prolonged action potential. Remember, the idea behind an absolute refractory period is you cannot get tension on top of tension, right? You cannot get an action potential on top of another action potential, which means in this case, right, our tension falls, right, while we repolarize up here, right, because the calcium's being removed from the cytoplasm and the sliding filaments are no longer grabbing onto each other and pulling, so tension falls back to a baseline, back to a minimum, right, before our next action potential is initiated, and then tension would rise again, right? So it separates our twitches in time. They cannot undergo wave summation and tetanus. There it is, folks. The prolonged action potential keeps the twitches from adding together, from being stacked one upon the next, right? Now think about this. In cardiac muscle, right, this contraction, right, is causing a pressure rise and the ejection of blood out into the arterial circuits. What's happening here, right, when it's relaxed? It's refilling, right? You have to have the relaxation phase in between the contraction phases so that you can reload the heart, if you will, with blood so that we can, when we contract again, we've got something to push. If the heart just contracted the way it does, in our wave summation figure here, if it just contracted and contracted and contracted harder, you'd move a lot of blood in the first, one contraction. The second contraction, stacked on top of the first without any relaxation in between, would move almost no blood. The third and fourth would move zero, right? And the fifth and the sixth and the seventh and the eighth, right? All of those subsequent squeezes aren't doing any work. So in cardiac muscle, it's highly adaptive to have that twitches separate in time so that we can fill that diastolic period, right? So we can fill in between those twitches. Okay. So that is explanation one for this prolonged plateau in the action potential, because of course we can't get another action potential and the twitch is going to occur and even end during that, at the end of that action potential so that they can't stack together like they do in skeletal muscle, where it is highly adaptive, right, for them to add together. Okay, what's the second rationale for our prolonged absolute refractory period? Let me clear some space here. Add another, clear half of this. We're going to show you another rationale for this avoiding, if you will, that's about right. Okay, so we've got this sort of arbitrary chunk of muscle. Let's think of it as ventricular muscle, right? And so we've got our action potential. So think of this as like the AV bundle. Remember the bundle of His? AV bundle, same thing. Right? So the AV bundle delivers an action potential to the ventricular mass. Well, the ventricles, especially, remember the left ventricle is like 70% of the heart mass, right? The right ventricle is about 20% of the heart mass. The atria, the other, whatever's left over, 10%, right? So first of all, this is like an enormous mass of tissue. Now, what I'm describing can happen in the atria, but it's much more of a problem if it happens in the ventricles. Okay, so we have the arrival of our stimulus, right? It happened up at the SA node initially, and eventually it's going to make it through the AV bundle, through the fibrous skeleton, right? Fibrous skeleton would be sitting right in here, right? The AV bundle passes through the fibrous skeleton, and we enter that stimulus into the ventricles. Now, there's a pathway, right? Basically, the conducting system sets up the roadways, down which this action potential will travel. But especially in the left ventricle, the cells are arranged in like a whorl, like a circle, right? Around a cone, essentially, with the cells sort of spiraling within that cone of the ventricle. And what that means is, right, so if we go down the septum here, right, our stimulus is going to travel up the walls and it's going to whirl around, which I'm not showing here, but has this potential to whirl around, right, sort of back towards the top of the ventricle. Now, when we get back to the top of the ventricle, right, because this happens very quickly, right? This cell to cell via the gap junctions, that stimulus is going to happen very quickly. I think that's important, right? That's coordinating the heart cells, that it travels rapidly. However, we want that stimulus to come back to the top up here, somewhere in here, right? Somewhere in here where you are still in your absolute refractory period, right? Because it comes back around and it hits this spot. Well, that cell's not going to do anything. It's already in the middle of its contraction, right? It's still contracting, it's still depolarized. That's good, right? Because our stimulus runs around the circuit and then runs into the wall, right? Runs back into where it started, but it can't re-stimulate. Okay? If our refractory period didn't exist, or if it were shortened, right? We're going to get, right? Let's go over here to the right, right? We would come down, right? This is what we don't want, right? So it would come down, it would travel the same circuit, right? And when it got back to the top here, if you were not refractory, in other words, if it hit over here somewhere, right? If it showed up in time here, can that cell respond? Absolutely. It's not refractory anymore, right? It's not in the absolute refractory period. And so it generates a new stimulus, a new depolarization wave, which would, right, that's the second dashed line. Start to travel around in the circuit again. And it gets back to the beginning. And guess what? It's not refractory again. It goes around in a circle. Right? It's called circus rhythm, kind of like the horses that ride around in a circle in the at the circus, right? In the rings. But it's really what's called a re-entry arrhythmia listed down here. Right? Arrhythmia means an abnormal rhythm. Re-entry because it's coming around and it's re-entering where it was supposed to be refractory, but it isn't anymore. Okay, so again, this long plateau phase is highly adaptive. Right? If this happens, if you get this re-entry arrhythmia, these circuits can become, well, first of all, you're going to end up with a ventricular heart rate that exceeds your SA node pace, right? And that's called a tachyarrhythmia. Tachy, like a tachycardia, means fast, right? So it's a arrhythmia that is essentially a fast heart rate. And in this case, it's going to be, the ventricles are going to be moving a lot faster, contracting at a rate that exceeds that of the atria. Well, that's not good, right? Because you're sitting there watching TV. You don't need a ventricular heart rate of 140 or 160 or higher, right? In some cases, these can be very high, high enough to the point at which filling is not effective, right? We're not filling the ventricles with enough blood, and cardiac output actually falls. So this can be actually quite dangerous. It can get even more dangerous when these circuits become disorganized, right? When sometimes these circuits, you end up with multiple circuits, multiple loops, right? You got a loop over here and you got a loop over here, like these tissue, right? Because all the cells have short refractory periods. And now you've got loops sort of starting everywhere. All right, well, now you have complete disorder, right? That is called fibrillation. And ventricular fibrillation, in this case, is very bad because now the muscles there's no coordination of activity and you're not generating pressure like sequentially. And so it's just sort of sitting there twitching, which means cardiac output, right, equals 0, right, or close to it because you're not coordinating and you're not contracting to squeeze the blood out of the heart. So ventricular fibrillation is highly dangerous, right? You need a defibrillator to sort of restart the electrical rhythm of the heart, the normal electrical rhythm of the heart. If that doesn't happen, right, death ensues in 3, 4, 5 minutes, right? So it's bad. Atrial fibrillation, not nearly as bad because again, the atria aren't pushing blood out into the circuits, right? They're just sort of facilitating what the ventricles do. They're helping to fill the ventricles. Does it reduce performance? Sure. The bigger danger of atrial fibrillation is that blood sort of doesn't get squeezed out of the atria and it can clot abnormally, in which case one of those clots can, it's called an embolus. One of those clots can sort of like fly off into the circuit and cause an embolism, right? An embolus is the clot. An embolism, like a pulmonary embolism, is when that clot gets lodged in a blood vessel and then blocks flow to that particular region, right? If it happens in the lung, it's pulmonary embolism. If it happens in the brain, right, it's a cerebral embolism, which is a stroke essentially, right? Or one type of stroke. Okay, so those it can still be dangerous, but not dangerous in a second, minute to minute way that ventricular fibrillation is. Now, the last thing I wanted to talk about were these channels called KATP channels. And KATP channels are generally protective because what they do is, and they're, in other words, they are regulated by ATP levels. And if ATP levels are low, what they do is they tend to shorten the plateau, right? They open, and again, of course, because it's a potassium channel, it would tend to shorten the plateau, right? Now, what that does, how's that adaptive? Well, it's helpful because it's reducing the calcium influx. It weakens the contraction, right? Which saves ATP. So it's kind of predictive. It's matching performance to the energetics available, the energy available. So that makes a lot of sense. However, if they are abnormally opened, right, to some dramatic degree, right, then we're in this realm where our absolute refractory period gets shorter, and here's our stimulus coming back, right? And so all of a sudden we increase the likelihood of arrhythmia, right? That reentry arrhythmia, because you've shortened your refractory period. When you get back around to the beginning, we're no longer refractory up here. We're here, right? And so they can be dangerous. What opens them? Again, they're normally regulated in a range that's safe, but cardiac ischemia, which causes it, so that's low blood flow, causes hypoxia, which is low oxygen, tends to open these guys. So low O2. Well, when does that happen in a heart? And I mean like abnormally low O2 levels. Well, that happens in the heart during a heart attack, right? When you're not perfusing a particular area. So there's this cascading effect, right? A heart attack is low blood flow because of a clot, right? So the tissue could be dying. That's causing great, if it's a big enough area, that could kill you right there, right? But it's potentially killing a chunk of heart muscle. Well, guess what? That low O2 is opening these potassium channels, which is creating this shortened plateau, which is tending to lead to arrhythmia, right? That tachyarrhythmia or even fibrillation, right? Again, when opened in excessive numbers, which of course would be very dangerous, right? And that's actually why a lot of people having heart attacks end up having to get defibrillated, right? If they don't have a fibrillation going on, right? They're just having a heart attack. Well, then they go in and they open up the vessel and, they're trying to reestablish blood flow. If it's severe and it's sort of, we've opened up the potassium channels, then they've got the lack of blood flow, and then stacked on top of that, they've got this reentry arrhythmia where the heart as a whole is no longer contracting appropriately, right? So it's sort of this cascading effect. One last thing about these potassium channels is this thing called commotio cordis. And it basically means like confused, like heart. These channels can get opened up by an impact, right? It happens mostly in children because they have less sort of structure, right? They've got less skeletal muscle. They've got, they're not as robust structurally as adults are. And if they get struck in the chest at exactly the wrong period in the electrical cycle, the cardiomyocytes, it can open these KTP channels, and it leads to those really, dire and disastrous events where a kid gets hit in the chest with a lacrosse ball or a baseball or something like that, and he goes into fibrillation for the reasons we just talked about. And sometimes defibrillation doesn't work because the channel effects are sort of prolonged. You can't get these darn channels to close soon enough before the heart can sort of like reset and go back to normal functioning. So it does sometimes lead to death. And it's just, there's nothing wrong with their heart. They were just fantastically unlucky. Um, anyway, so another good reason to learn CPR and right and be able to try to maintain blood flow even though the heart's not working for a prolonged period, right? Hoping those KATP channels will close and we can restore normal heart function. Okay, so there's the importance of the absolute refractory period, right? Avoiding wave summation and tetanus would be the first big one, right? Because that would lead to a cardiac output of 0 if you had tetanus in the heart muscle. And the second one is avoiding this re-entry arrhythmia problem, and potential fibrillation and tachycardia or tachyarrhythmia. Sorry, both of which are bad and worse. Okay, and then of course these KTP channels, which adaptively functional to help match energy supplies to heart performance, but then can become maladaptive if they get opened up during these pathological conditions like coronary ischemia, low blood flow during a heart attack, or this commotio cordis effect when a kid gets hit, usually a child gets hit in the chest at just the wrong instant of the cardiac cycle to open those channels. All right, we'll stop there.